I'm Mark Arenes, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 13. Given these 50-digit numbers, find the first 10 digits of their sum. This is a list of 100 numbers, and we want the first few digits of their total. You might naively write a program in your favorite programming language to simply read in these 50 lines from a file and add them up in one variable, but that might not work depending on your choice of language. Many programming languages use 32-bit or 64-bit integers, and this sum may very well exceed the limits of such types. Assuming we're talking about signed arithmetic, a 32-bit integer can store numbers up to 2 to the 31st power minus 1, represented with a sign bit of 0 followed by 31 ones. Likewise, a 64-bit integer can store numbers up to 2 to the 63rd power minus 1 in a similar way. Let's try to approximate how many bits it would take to store the sum we're looking at in full. The maximum value of a 50-digit number must be less than 10 to the 50th power. We have 100 such numbers, so our sum is bounded above by 100 times 10 to the 50th. To figure out how many bits it would take to store a number in base 2, we take the binary logarithm, or log base 2, of the number, and add 1. At this point, we could just use a calculator, but we can also simplify this by hand. The logarithm distributes over multiplication, turning it into addition in the process, and then our exponent moves down to the front of the log. Log base 2 of 100 is between 6 and 7, since 2 to the 6th power is 64 and 2 to the 7th power is 128, with 100 sandwiched between them. Likewise, log base 2 of 10 is between 3 and 4, since 10 is sandwiched between 2 to the 3rd and 2 to the 4th. So our quantity is somewhere between 156 and 207. We can check our work with a calculator and find that the actual value is 172.7. That means it would take 173 bits to store our sum in the worst case. The sum can't be stored in either 32-bit or 64-bit integers. Fortunately, many languages nowadays natively support big number arithmetic. This means that, when needed, such languages will gracefully switch from a fixed-size representation of integers, such as 32 or 64-bit integers, to a representation that varies in length and keeps track of its own length. With variable length integers, the only limit to the magnitude of your integer is how much memory the operating system is willing to give you. Raku is one language that has built-in support for big number arithmetic. Raku is a relatively new scripting language heavily inspired by Perl, and we've used it once before in this series. We can solve this entire challenge in Raku in one incredibly short, snappy line of code. Let's assume that the 100 numbers are in a file called input.txt. We take that file name, treat it as an I/O object, and get a list of the lines of the file, which we immediately sum. Once we have the sum, we take the first 10 characters and output them. There's a lot of subtlety here. First, most built-in functions in Raku happily coerce between strings and numbers, so we seldom have to do an explicit conversion. Lines returns a list of strings, which sum happily coerces into a list of numbers before summing. Likewise, substring coerces our sum back into a string before taking characters. Additionally, we never had to tell Raku that we wanted to use big num. This language is smart enough to tell when we want to use integers, which are always completely precise, and when we want to use a floating point number, which is an approximation of a real value. Finally, substring takes a range, which indicates the part of the string we want. Caret 10 is a shortcut, which means the range from 0 up to and excluding 10. So substring caret 10 gets the first 10 characters from a string. This is short and to the point, but perhaps it seems too easy. After all, if we can simply find a language that has big num support and knows how to add numbers, we have our solution, and we can do that in nearly any language. So today, we're going to solve this problem in a language that doesn't know what big nums are. In fact, we're going to solve this problem in a language that doesn't know what numbers are. We are going to teach the computer how to add. With that in mind, we're going to rewrite our Raku program a couple of times. First, let's pretend that we don't know how to add full numbers, but we do have a way to add single digits. We're going to rewrite our Raku program to teach the language how to add multi-digit numbers, given an oracle that adds individual digits. First, let's write our so-called primitive operations. We'll have two primitives, one that increments a number by 1, and the other that adds two single-digit numbers together. Both of these functions will cheat right now and use real Raku addition, but we'll fix that in a few minutes. Next, we write an add numbers function, which adds two numbers together. We're going to do this the way a human would. We'll take the rightmost digits and add them together, then the next digits, then the next, and so on. As we proceed, we'll keep track of the so-called carry digit. If the two numbers we just added sum to greater than 9, then we add 1 to the next digits to compensate, effectively carrying over a 10. We take our two arguments a and b as copies, so we can mutate them inside the function. Then we create a string to store our result, and our carry digit starts out false since the rightmost column never has a carried value. We're going to loop until we run out of digits in both a and b, so loop as long as at least one of a or b has digits left. Inside the loop, if one of the numbers happens to be empty but the other isn't, set the empty one to 0 so that we have a digit to add. Next, we get the final digit of each number. Before, when we called substring, we passed it a range object. The substring function is highly polymorphic. If given a range, it returns the characters in that range. If given a number, it returns the characters starting at that position and going to the end of the string. Now you might be saying, but star minus 1 is not a number. And you're correct. Many languages, most famously Python, extend indexing and slicing operations to support negative indexing. In Python, we can index into a string or a list using a negative number, and doing so will count from the end of the list rather than the beginning. Raku takes a different approach. In Raku, if you want to index from the end of a list, you can supply substring or any of the other indexing functions a unary function as argument. When given a function as argument, substring passes the length of the string to that function and uses the resulting number to index into the string. Here, we pass substring a lambda function. It takes one argument, called len, and returns len minus 1. When we call substring like this, it invokes our lambda function with the length of the string as its sole argument. The lambda returns the length minus 1, and substring uses that to index into the string. What we've written in our code is exactly the same. The star, when not used to indicate multiplication, is read as whatever, and begins a compact syntax for lambda function. So star minus 1 reads as a lambda function of one argument, which subtracts 1 from its argument. All of this is to say that, to do negative indexing in Raku, simply put a star in front of the otherwise negative index, and the whatever syntax will do what you expect on its own. Once we have our digits, we add them together using our magical oracle add function. Then, if we had a carry digit from the previous operation, we increment our total one more time. We take the final digit of our total, which is a number from 0 up to 19, and prepend it onto our result string. Tilde is used for string concatenation in Raku, and like most operators, it will happily coerce its arguments if they aren't already strings. We set our carry flag to true if the total number is at least 10. Then we chop off the last digit of each of our input arguments. Chop is a built-in string method in Raku that removes a single character from the end of the string. The dot equals syntax, like any other compound operator, applies the method to the argument on the left, and then assigns the result back to the argument on the left. Finally, at the end of our loop, we prepend a 1 to our number if we still had a carry digit from the final column of computation. Then we return our result. Back in our main code, we replace the sum call from before with a general purpose reduce call. Reduce is a fold operation that takes a binary function, add numbers in our case, and applies it pairwise to elements of the input list until there's only one value left. The ampersand sigil indicates that we're accessing a first-class function object. Now, we can add numbers based on just two primitive operations. But our primitive operations are still cheating. We want to remove every occurrence of the plus sign from our program. Let's start with increment. There's 18 possible inputs to increment, since the largest our total digit can possibly be without the carry flag is 9 plus 9, or 18. So let's enumerate them. Given is Raku's version of a switch statement, so we'll simply check our input against each integer from 0 to 18. When we find a match, we return the pre-computed value. Now at this point, you may be wondering if I'm crazy enough to enumerate the 100 possible ordered pairs of digits that we might need to add together. And indeed, that's exactly what we're going to do. There's 100 cases. We could cut it roughly in half if we ignore the order of our inputs, but we're going to brute force all 100 so it's easier in our target language in a few minutes. It takes a bit of time, but it's not a difficult computation. So with a bit of patience, we get there in the end. And now we've successfully converted our one-line Raku program into a 151-line solution that doesn't know how to add numbers and runs slower. I consider that a success. We're ready to translate this into our target language. This week, we'll be solving Project Euler in GNU sed, the Linux Stream Editor command line tool. You've probably used sed in the past as a quick and dirty regex substitution tool. You may have potentially used it as a character transliteration tool as well. What a lot of people don't know is that sed isn't just a regex tool. It's a full-featured programming language in and of itself, capable of control flow, looping, branching, and doing arbitrary text manipulation. When you feed sed a command directly from the command line, you're implicitly running a single command program. It's as though you created a script file that had that one line in it and told sed to execute that script. This is the most common use case, which is why sed provides it directly as a convenience. For our purposes, of course, we'll be writing a script file consisting of several commands in sequence. When a sed program is run, it takes input in the form of a file, often from standard input. Sed is line-oriented, so for each line of the input file, it runs the entire script in order. By default, sed runs in print mode, which means when it's done with each line, it will automatically print the line, potentially having been modified by our script, to standard output. We'll be using sed in non-printing mode, which is activated by passing the -n command line flag. In this mode, sed will still run our program once per input line, but it will only output a line when we explicitly ask it to with a command. Now let's talk about the commands we'll need today. This won't be a comprehensive discussion of everything sed is capable of. If you're interested in a full introduction to everything sed can do, I recommend Bruce Barnett's Grimoire, which is an amazing reference and is where I personally learned about sed when first starting out with Linux. First, we'll talk about the most commonly used sed command, substitution. When a line of a sed program starts with S, we perform a substitution command. The S must be followed by a delimiter, most commonly a forward slash. Then what follows is the string to search for, the delimiter again, the string to replace it with, and finally the delimiter one more time to terminate. When this command runs, the first occurrence of the left-hand string will be replaced in the current line with the right-hand string. If we want to replace all occurrences, not just the first, we can suffix our substitution command with the G flag, which stands for global replacement. Substitute also accepts other flags that we won't need today, such as I for case-insensitive searching, or 2 to only replace the second occurrence of the pattern on the line. But I've oversimplified things a bit. The left-hand string isn't just an ordinary string. It's a special kind of string called a regular expression. A regular expression, or regex for short, is a compact syntax for describing patterns in strings. Our left-hand substitution argument isn't just a literal string to be matched. It's a pattern syntax that describes the type of string to be matched against. Most characters in a regular expression are matched literally. So a literal lowercase a in a regular expression matches only a single literal lowercase a in our input string. This is true of letters, numbers, and many symbols. We call the characters which have special semantic meaning in regular expressions meta-characters. There are a couple of exceptions to this. First and foremost, the dot matches any single character except new lines. To match a literal dot, you need to escape it in the regex with a backslash. The caret is only a meta-character at the very beginning of a regex. When supplied at the beginning, it indicates that our pattern only matches at the beginning of the input string. So the pattern burger would match the second half of the word cheeseburger, but the pattern caret burger would only match the word burger if it starts the string. The $sign works similarly at the end of a regex to indicate that we should only match the end of the string. Square brackets can be used to enclose a character class. A pair of square brackets always tries to match exactly one character, and the character can be anything inside the brackets. So the pattern bracket ABC close bracket matches one character, which can be either A, B, or C. The referent inside the brackets can also be arranged. So A-Z inside brackets matches any ASCII lowercase letter, and 0-9 inside brackets matches any ASCII digit. Finally, if the character class begins with a caret, it's a negative match. So caret ABC matches one character that can be anything except the lowercase letters A, B, and C. Likewise, bracket caret 0-9 bracket matches any one character that is not an ASCII digit. Regex also gives us several modifiers that match multiple characters at once. The star, often called the clean star, takes a pattern on its left and matches 0 or more copies of it. So A star matches any possibly empty sequence of the letter A, while 0-9 star matches any sequence of ASCII digits. Backslash plus is a variant of the clean star that must match at least once. So 0-9 backslash plus matches sequences of ASCII digits but fails if there are no ASCII digits at the current position. If you've used regular expressions in more modern tooling like Python or Perl, you're probably surprised to see the backslash here. Sed is an older tool and is, by default, very conservative about what it considers a meta-character. So many things we take for granted in regular expressions today, such as the plus, curly braces, and even parentheses, must be escaped with a backslash to be considered as a meta-character in said basic regular expression syntax. Similarly, we can match a pattern a specific number of times, or a range of numbers of times, using curly braces escaped by backslashes. Inside the curly braces, we indicate the number of times we want to match. So A to Z, 5, matches a sequence of exactly 5 uppercase letters. We can also put 2 numbers in the braces to indicate a range. So this pattern matches between 5 and 8 uppercase letters inclusive. If we leave off the first term in the range, it defaults to 0. And if we leave off the second, then we opt not to have an upper bound. That is, comma 5 matches up to 5 ASCII capital letters, and 5 comma matches at least 5 ASCII capital letters, with no upper bound. All of these modifiers are by default greedy. That means that given the option, they'll always consume as many characters as they're allowed to. As a concrete example, the pattern A star will match 0 or more of the capital letter A. When this pattern attempts to match part of our string, it will look for capital letters A, and will try to take all of them. If something later on in our pattern fails, then the regular expression will backtrack and try to match fewer characters, but that only happens after trying to match everything greedily first. Finally, we need to talk about capture groups. By enclosing part of a regular expression in backslash escaped parentheses, that part of the regular expression is considered a capture group. When we later go to perform our substitution, we can reference that capture group as a sort of variable using a backslash followed by the 1 based index of the group in the pattern. Let's take a look at an example. The pattern in this substitution will match any sequence of 1 or more digits. Then, when we perform our substitution, we take the first capture group and wrap it in curly braces. The first capture group consists of the thing inside the first set of parentheses, which in this case is the digits we matched. So this substitution would make the following replacements. Note that we use the global modifier flag to ensure every sequence of digits gets updated, not just the first. The character ampersand can be used in the replacement portion of a substitution, and it acts as a sort of special capture group that refers to the whole match. So this pattern would parenthesize any sequences of letters in our input. If you're not a fan of the maze of forward and backward slashes in the pattern and replacement syntax, we can make this a bit more readable. Remember, we can use virtually any character as the delimiter, not just the forward slash. So you might prefer to use the hash sign. We can even use letters or numbers as our delimiter if we're feeling particularly sadistic, or even whitespace for that matter. We'll use other symbols when they add to readability today, but we'll default to the forward slash when it makes sense to do so. The next command we'll need is perhaps the most basic. The p command takes no arguments and prints the current line. Remember that by default, sed prints every line as a rule. So without any command line flags, the sed program p will print every line twice. Once for our p command, and again by the default rules of sed. With the -n command, the program p will simply print its input unmodified, acting like the cat program. The p command isn't tremendously useful on its own, but it becomes more handy when used as part of an address. Any command in sed can optionally be prefixed by an address, which indicates which lines it should apply to. Any lines which do not match the address will skip over the command that the address precedes. The simplest kind of address is a numeric address. When a number precedes a command, it's treated as a line number, and runs the command only on that line of the input. So 1p is a program that prints out the first line of a file, and 10p would print the 10th line. A $sign as a line number refers to the last line of the file, so the said program $p prints the last line of the file. Addresses can also be specified as ranges, separated by a comma. When a range is specified, it's presumed to be inclusive on both boundaries, so 1, 10p prints out the first 10 lines of a file. Similarly, 20, $p prints out the tail of the file starting at line 20 and going to the end. Remember that addresses can precede any command, not just print commands. So this program, for example, prints every line of the file, but on the first 10 lines, and only the first 10 lines, the name Fred will be censored and replaced by 4 stars. The next kind of address is a regular expression. If our address begins with a forward slash, followed by a regex, then another forward slash, then the following command will only run on lines that match the regular expression. We can use this to emulate the behavior of the grep command line tool. The program EP will print only the lines of the input that contain at least one capital letter E. Finally, if you want to group multiple commands under a common address, you can use curly braces to do so. For example, this program will capitalize any A's, B's, and C's on the first 10 lines, leaving all of the other lines alone. Note that we can also leave comments in a sed script, similar to most shell utilities, by prefixing the comment with a hash sign. Next, we'll discuss one of the lesser used features of sed, that being the ability to branch. Sed has the ability to set labels and perform go-to style jumps to those labels from anywhere in the program. Labels are set with a colon followed by the name of the label. Then, at any other point in the program, the B command, short for branch, followed by a label name, will jump to that label. A branch command on its own merely forms an infinite loop, but branch instructions qualified by an address can be used to implement arbitrary control flow. We'll use this to implement a rudimentary form of functions in our sed program. Sed has another go-to-like command, which will be convenient in our use case in a moment. The T command, short for test, is followed by a label name, similar to the branch command. When the T command is encountered, it jumps to the given label, but only if the last substitution command we performed successfully found a match. To see why this is useful, suppose we want to take an input string consisting of only open and closed parentheses, and we want to remove any balanced sets of parentheses, leaving alone any parentheses that are not balanced correctly. We can remove the innermost nested parentheses fairly easily, but this substitution alone will not remove all nested parentheses. In fact, there is no singular regular expression that can do so. This is a consequence of the pumping lemma for regular expressions, which defines some limitations as to what regular expressions are actually capable of. However, we can remove nested parentheses in a sort of loop like this. We begin with a label called loop. Then we try to remove parentheses that have nothing in them. If we succeed in this, then we jump back up to the label and do it again. If we don't find any correctly matched parentheses, then the substitution fails, we proceed to the final line of our program, and we print the result. Now, there's one more puzzle piece we're going to need to discuss before we can talk about our actual algorithm. When I mentioned that sed is going to run your entire program once per line of input, I was oversimplifying things a bit. It's true that by default, sed will run your program once per line of input, but it's also possible to change this behavior. There are several ways to do that, but the one we'll need today is called the capital N command. When the capital N command is encountered, sed will read the next line of input, append it to the current line, and continue executing your code right where it left off. Because we've used a capital N here, this program will end up processing the lines of its input pairwise, and we'll group them together with the word and in between. Suppose we gave this file as input. The program starts by reading Alice in. Then we run the N command. This reads the second line, Bob, and continues executing. After this, the line of input we're operating on consists of the name Alice, followed by a new line, then the name Bob. We run a substitution to replace the new line with the word and. Then we print it. This prints the string Alice and Bob on one line. Once we're done, sed will read the next line of input and start over. We've already read Alice and Bob, so the next line is Charlie. The end command will read Dave, and the second line will print as Charlie and Dave. Then the third loop will print Eve and Frank, and the program will terminate since we've reached the end of our input file. By the way, I've been vaguely using the term current line to refer to the string of input we're operating on. Really, this current line is a sort of variable. Sed calls the string it's currently operating on the pattern buffer, and all commands in sed operate on this buffer. Now we have all of the tools we need. Let's talk about our approach. First, we'll store our 100 numbers in an input file. We're going to add one line to the end of the file, which consists of only a 0. This is merely a sentinel value to indicate to our sed program that we've reached the end. Now, sed has no concept of numbers, or of addition, so we're going to have to use regex substitution to perform arithmetic. On top of that, sed has no concept of variables, so everything we do is going to take place in one string, our current line or pattern buffer. Here's how we're going to add numbers. Sed implicitly reads the first line as input. We're going to read the second, so we have both numbers in our pattern buffer with a new line in between. Now we're going to do some regex substitutions to remove the new line, wrap the input in parentheses, and put a plus sign in the middle. Note that the plus sign isn't anything special in this context. Sed still doesn't know how to add numbers, and we could have used any non-numeric character here as our separator. We simply chose the plus sign since it intuitively looks like a mathematical expression to a human reader. Now comes the real magic. In our Raku program, we wrote 100 different cases to cover all the possible ways to add two single-digit numbers. Instead, we're going to write 100 regular expression substitutions to do the same. Each regex will match exactly the pattern we have here. A pair of numbers in parentheses separated by a plus sign. Each pattern will look for the final digits in those respective numbers. Then the substitution will replace this pattern, leaving alone all but the last digit, and moving the last digit out of the parentheses. After one iteration, our string will look like this. Then we'll run this in a loop until there's nothing left inside the parentheses. Finally, when there's nothing left in the parentheses, we simply perform one last regex to remove them. And now we've added our two numbers. After this, we'll grab the next line and repeat the process. We haven't talked about carry digits yet. If two digits of a number sum to a value greater than or equal to 10, we need to make a note in our output somehow that the next digit should be incremented. We'll indicate this by placing a C to the left of the digit we just produced. Then, as a separate set of substitutions, when we see a C to the right of a digit, we'll increment the digit. So 0C will become 1, 1C will become 2, and so on up to 8C, which will become 9. A 9C will become C0, since 9 plus 1 produces a carry digit of its own, so we need to pass that on to the next number. And as a final special case, a carry on the far left of a number will be replaced by a 1. Let's see an example. First, we read in our two lines of input. We put a plus sign between them, then we add our first digits. 1 plus 2 is 3, so after one step, our pattern buffer will look like this. Now, our next digits are 3 and 8. 3 plus 8 is 11, or more precisely, 3 plus 8 is 1 with a carry digit, so we write it as C1. Our pattern buffer consists of the remainder of our addition operation, followed by C13, indicating a number ending in 13 and a carry digit that we haven't yet resolved. Our next digits are 0 and 1. 0 plus 1 is 1, so we move it to the outside of the parentheses. Now, we have a digit that has a C to its right. That means we need to increment that digit and get rid of the carry flag. Our next digits are 5 and 5. 5 plus 5 is 10, or 0 with a carry, so we write it as C0. Then we add 3 and 6, which makes 9 with no carry. Get rid of the parentheses, since we're out of digits. Now, I see a number followed by a carry. We increment the number and remove the carry, but incrementing 9 produces 10, or 0 with carry, so we replace 9C by C0. Finally, we have a carry on the far left of our input string, so we replace it with a 1. And that tells us our sum. 35,031 plus 65,182 is 100,213. And that's our algorithm. It's time to write some code. Let's get started. First, we'll write our main loop. This loop will be responsible for reading the next line of input in, setting up our parentheses and plus sign syntax, and then calling out to another label to perform actual addition. Inside our main loop, which we aptly name main, our pattern buffer currently consists of the sum of numbers we've seen so far. If this is the first iteration, this is just the first line of input, which was read in by sed automatically. If this is a later iteration, it's the value left behind in the pattern buffer by our previous iteration. We start by reading in the next line of input with capital N. Then we check if we've encountered our all zero ending value. If the line we just read in consists of only zeros, then we know we've hit the final line, so we can jump to our end label, which we'll write in a moment. Remember that, after reading in our new line with capital N, the pattern buffer consists of two separate lines, separated by the new line character. Our regular expression, which checks for the sentinel 0 value, checks whether our pattern buffer contains a new line, followed by one or more zeros at the end of the input. If we haven't reached our sentinel value, then we replace the new line with a plus sign, then we parenthesize our input. Once our pattern buffer is in the right format, we jump to our start label. This is where we'll actually do the addition operation, and we'll get to it in a minute. Our start label will always jump back to main when it's done. Now we write our end label, which is fairly simple. If we branch to the end label, then our pattern buffer contains two lines. The first is our total sum, and the second is the 0, which was the final line of the input. First, we remove the new line character and everything after it, getting rid of the sentinel 0 value and leaving only the full sum. Then we take the first 10 characters of the input. Recall that our original problem description only wanted the first 10 digits of the sum. To do that, we perform a single substitution, which matches the whole string from start to finish. As it does so, we place the first 10 digits in capture group 1. Then we replace the whole line with just capture group 1, which removes all but the first 10 characters. Finally, since we're running this with -n, we print out our pattern buffer explicitly with the p command. That's our main loop. Now let's get to the hard part, actually adding two numbers. We'll call our adding label start. This label will be responsible for two things. First, if it detects that we've finished adding our numbers, it'll branch back to main and read in the next line. If not, we perform one step of the addition operation, which might be a carry or a digit, and then we jump back up to start to continue. Before our start label, we do an unconditional branch to main, since we'd like our program to start at the main label. Now, inside our start label, we first want to check if we're done adding. We're done adding if the only thing on the current line is numerical digits. That is, there's no parentheses, plus signs, or unresolved carry digits left. If that pattern matches, then we perform a substitution to remove any leading zeros from the number, then we branch back to main and continue on to the next line. If not, we begin our addition rules. Rule number 1. If there's a single number in parentheses and no plus sign or other number, we can remove the parentheses. This will happen if one side of the addition operation has more digits than the other. After each attempted substitution, we call t start. That is, every time we successfully perform a substitution, we jump back up to the start label and check if we're done again. Now we deal with the identity cases of addition. If our pattern buffer is of the form 0 plus some number, or some number plus 0, we can simply remove the 0 part. This involves two substitutions, one for a 0 on the left-hand side and one for a 0 on the right-hand side. Next, we deal with our carry digit. Remember that if we add two digits and we need to carry a 1 to the next digit, we'll put a C immediately to the left of the number we just produced to indicate that a carry needs to be applied to its left. Here, we'll deal with the C value. The pattern 0C should be replaced with 1, 1C should be replaced with 2, and so on. Remember that 9C is replaced by C0 since the carry digit moves to the left when we carry on a 9. Likewise, a C at the beginning of a number is replaced with a 1. The beginning can occur if the C is preceded by an open parenthesis, a plus sign, or the beginning of our entire pattern buffer. Now, if one number was longer than the other, the shorter number will run out of digits faster. If that happens, our pattern buffer will contain a parenthesis character next to a plus sign. When we encounter that situation, we want to insert a 0 between the parenthesis and the plus sign. On the next iteration, we'll use our identity rules to replace 0 plus number, or number plus 0, with the non-zeroed input. Now we get to the real meat of our program, which is the 100 possible ways to add two one-digit numbers. We're going to write 100 of these, so let's break down the first one. This is the result of 0 plus 0. This pattern is going to match a pair of numbers in parentheses. For the first number, it must end in a 0, and all other digits are grouped into capture group 1. Likewise, the second number must also end in a 0, and all of its digits are grouped into capture group 2. The replacement part of our substitution will give us two numbers in parentheses, followed by a 0. The two numbers inside the parentheses are our two capture groups, those being the original two values with the final digits truncated off. Then, we do t start to jump back up to the top of the loop if we successfully did a substitution. There's no carry digit in this example, but if there was, it would involve placing a C immediately after the closing parenthesis. Now we do that 99 more times. It's not exciting, but it's honest work. When we get down to the bottom, we're done. That's 274 lines, and it's our entire sed program, which is capable of adding numbers in a loop, despite sed not knowing what adding or numbers are. We can run this with the -n flag and feed it our input file, terminated by the sentinel 0 value, and it prints out the first 10 digits as intended. And this solves Project Euler problem number 13 in sed. Tune in next time when we take a look at problem number 14 in Smalltalk.